The Cathedral, 30 feet tall, about 1,000 tons. 4 cylinders, the biggest of them 97 inches across, turning at 75 revolutions a minute. And that is one engine. There were 2 of them in the bottom of the Titanic. It is a triple expansion steam engine, and the name is the trick. Steam arrives at 215 pounds of pressure, enters the smallest cylinder and shoves the piston down. But it is not finished. That exhaust, still under pressure, gets piped into a bigger cylinder and does the job again. Then into 2 bigger ones still, a third time. Same steam, 3 helpings. The cylinders grow because the steam is expanding and weakening, so you need more piston area to keep the push the same. So why is it dead? The turbine? Above about 14 knots, it got more power out of less weight, and this engine had a ceiling written into its geometry. Past an expansion ratio of somewhere between 16 and 20 to 1, the last cylinder becomes a thing you cannot build. And those 2 engines exhausted into a low-pressure turbine on the center shaft, drinking their leftovers. Its own replacement was riding along in the same room. The hot bulb. To start this engine, you need a blowtorch, held against a steel knob on top of the cylinder until it glows dull red. That takes minutes, and on a big cold one, the best part of half an hour. Who signed that off as a way to leave harbor? Bolinder of Stockholm built these, and in the 20s they had around 80% of the world market. The knob is the point. A real diesel squeezes air 15 to 20 times over to light fuel by itself. This one squeezes 3 to 7. Nowhere near enough. The rest comes from that uncooled bulb, which you heat by hand and combustion keeps hot. And starting it was dangerous, but not the way people tell it. You did not hand crank these. You pulled a sprung pin out of the flywheel, primed the pump, and kicked the pin round. Get the fuel wrong, and it backfires hard enough to break your ankle. Boatmen opened the doors first, so a kickback threw you into the water, not the woodwork. And the bulb is also the ceiling. It has to stay hot, so you cannot cool it, and you cannot raise compression without it firing early. That pins it at a few hundred revs while a proper diesel spins to 2,000. It's shipped with instructions for falling in the water. The Headless One. This engine has no cylinder head. None. One test cylinder of it stands 32 feet tall and weighs 100 tons, and where the top should be, there's another piston coming the other way. Doxford of Sunderland built it, and the fire happens between the 2 piston crowns as they rush at each other. No head, no valves, nothing on top. So how does it breathe? The pistons do it themselves. The upper one uncovers exhaust ports first, letting the pressure blow down, and a moment later the lower one opens the scavenge ports, so air sweeps straight up the bore. Which leaves the other problem. The lower piston drives down to the crankshaft normally. The upper one cannot because the lower one is in the way. So they bolted it to a yoke above the cylinder and ran 2 enormous side rods down the outside into the crankcase. 3 crank throws per cylinder, the outer pair half a turn from the middle, so both pistons move together. Now the failure, and everybody gets this one wrong. The engine did not break. Nothing in the record blames the pistons, the side rods, or the heat. British yards simply started building Swiss and Danish engines under license, and Doxford's last new design sold exactly 0. It did not lose an argument. It lost a country. The triangle. Everything so far has filled a room. This one you could carry down to the water, and no pistons at all. It is a Yanmar rotary outboard, sold from 1972. 330 cubic centimeters, 28 horsepower. Inside is a triangular rotor turning in a housing shaped like a peanut. Its 3 tips ride on sprung seals, cutting the space into 3 chambers, and each one is at a different point in the same cycle. One drawing in while the next is squeezing and the third is burning. And the rotor does not even spin on the center of the shaft. It orbits an offset lobe at a third of the shaft speed, which is a lovely idea for an outboard, because an outboard hangs off the back of a boat where every pound is punished and there is nothing reciprocating in here to balance out. And then it drank. Rotaries are thirsty, and in 1973 the price of oil went through the roof, which turned an annoying flaw into an unsellable one. Sales stopped in 75. The Americans tried the same trick, and their rotary outboards won a Grand Prix and 2 national championships without ever being sold to a customer. A Japanese history says one turned up in Wankel's own collection. The steam diesel. 1 piston, with two completely different kinds of engine pushing on opposite sides of it. This is the Scott Still built in Greenock and fitted to a cargo ship called the Dolius in 1924. On top of the piston, it is an ordinary diesel. Fuel burns, piston goes down. Underneath that very same piston, it is a steam engine, and the steam shoves it back up. And the steam is free, raised by waste heat off the exhaust and the cooling jacket of the diesel above it. An engine running on its own leftovers. It was claimed to reach 40% against about 34% for a good diesel. On the water, it was a nightmare. The same gland that let steam reach the underside of the piston let oil into the steam system and steam at full boiler pressure down into the crankcase. Cylinders cracked. The Dolius cracked a crankshaft after 3 years, and you had to man it with engineers holding both a steam ticket and a motor ticket, which ate the saving in wages. Then the turbocharger arrived and recovered the exhaust half of that heat with no boiler and no second fluid. One line survives from the men who ran it. Young engineers became old men in the course of a voyage. 2 ships got one. Nobody ordered a third. The bouncer. Find the crankshaft on this one.
Go on.
There is not one, and it took 400 pounds of pressure in compressed air just to get the thing started. This is a 1950s gas generator by Cleveland Diesel. 2 pistons facing each other, only this time there is nothing underneath them. Diesel fires between them and blows them apart, and as they fly outwards, they squash air in bounce cylinders at each end. That trapped air is a gas spring and it throws them back in. A linkage keeps the 2 halves in step. Nothing drives them. And the same lump is also the air compressor. 3 jobs, 1 part. And it produces no shaft power at all. All it makes is hot, high-pressure exhaust piped to a separate turbine, and the turbine turns the propeller. They put 6 into a tired Liberty ship and took a 10-knot freighter to over 15 knots on trial. So what went wrong? Nothing fixes the stroke. On a normal engine, the crank decides where the piston stops. Here, one firing that runs slightly hot changes the bounce pressure, which changes the next stroke's compression ratio, which changes the firing after that. The French ran a fleet of them and logged 250,000 hours like this. They were never quite tame. The Blur. 44 tons. 2,100 horsepower. 34.5 knots in 1897 out of a hull 9 feet wide. Except that on her first outing, Charles Parsons Turbinia was a humiliation. The usual figure is just under 20 knots against an expected 30. All that power going in, and she would not go. Spin a propeller blade fast enough, and the pressure on the back of it drops below the vapor pressure of water. And when pressure falls that far, water boils. Not because it is hot, because it is no longer being squeezed. So the blade thrashes inside a pocket of steam it made itself, gripping nothing. That is cavitation, and Parsons built the world's first cavitation tunnel to look at it. The fix was to stop asking one propeller to do everything. 3 turbines, 3 shafts, 3 propellers on each shaft. 9, each loaded so lightly the water never boiled. Then he ran it through the assembled fleet at Queen Victoria's Jubilee Review. The popular version says he gate crashed. A man who was aboard said the run was invited. What is beyond doubt is that the picket boat sent to head him off could not catch him. 2 turbine destroyers were in the water within 2 years. Her hull is still in Newcastle. The Windbag, 4 pistons, each one 14 feet across. Said to be the largest pistons ever fitted to any engine anywhere, turning at about 10 revolutions a minute. The ship was called the Ericsson after the man who 9 years later designed the Monitor. And there is no water in this engine. No boiler, no steam. It ran on hot air. Air was drawn in, compressed, and passed through a regenerator, an insulated box the size of a mattress packed with fine wire, then heated over a furnace until it expanded and shoved that piston along. On the way out, the spent air went back through the same wire and left its heat behind for the next stroke. Ericsson claimed it handed nearly all of it back, so the furnace only had to top up the losses. Enormous power. Almost no coal, and that sum cannot work. The job of the power stroke is to turn heat into work, and heat that left as work is not still in the exhaust waiting to be handed back. A regenerator recycles the heat you were about to waste, not the heat you used. In fairness, thermodynamics barely existed when he built it. It managed half the speed of an ordinary steamer, was knocked flat by a squall, and sank. They raised it and gave it a boiler. The atomic, 300,000 nautical miles on one load of fuel, 8,500 tons of cargo, and a nuclear reactor in the middle of it. This is the NS Savannah, and in 1962 she was the world's first nuclear merchant ship. The reactor heats water under so much pressure it cannot boil. That water boils a second loop into steam, and the steam drives 2 turbines geared down to one shaft. It sits in a 50-foot containment vessel behind 500 tons of shielding. And here is what went wrong. Most of the weight and volume of that plant is not machinery. It is shielding. Dead mass amidships in exactly the space a cargo ship earns its living from. And because it was a showpiece rather than a freighter, they gave it a rounded hull that is awkward to load. It ran about $2 million a year worse than an oil-burning ship. And the timing of what happened next is cruel. They pulled it in 1971 when oil was $20 a ton. By 1974, it was $80. It was named after a ship, the Savannah of 1819, the first steamship to cross the Atlantic. Its engine ate the cargo space too. Same name, same mistake, 143 years apart. If you want more machines somebody genuinely built and then had to explain, there's a subscribe button and a lot more scrap where this came from. Send it to the Scrapyard.